everybody, welcome back to Trigonometry. Today we're in section 3.1 and we're going to be talking about radians for the first time. In this section we will learn about radian measure, so we'll get a definition for radians and we'll kind of get a feel for how big a radian is. And we'll talk about how to convert between degrees and radians. And we'll also get just a little bit of practice evaluating trig function values of angles in radians. So let's get started. So first of all, what is a radian? Well, an angle that has its vertex at the center of a circle that intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. So you can see on the diagram here, we have a circle on a coordinate system, and the circle has its center at the origin. And you can see the radius here. And now what's special about this angle is that the arc of the circle that this angle cuts off is exactly the same length as 1 radius. And so we would say that this angle has a measure of 1 radian. Now you can see right away that a radian is much bigger than a degree. It takes 360 degrees to make the whole circle, but look what a big chunk this radian is. So there's no way 360 of these fit in a circle. So if you had to guess about how many degrees this angle is, you would probably say it looks to be about 60 degrees, and that would be very close to the right answer. It's not exactly 60, but for just eyeballing it, 60 degrees is a pretty good estimate. We'll get a little more exact in a few minutes. Now look at this second diagram. This angle has a measure of 2 radians, and you can see here that we have 1, 2 radius lengths that this angle cuts off on the circle, and so this angle has a measure of 2 radians, and it looks to be close to 120 degrees, but of course it's not exactly 120 degrees. It is a little short of that, but it is exactly 2 radians in measure. And then look at the third diagram. This angle has a measure of 3 radians, and you can see it's just a little short of 180 degrees. So 3 radians is just short of 180 degrees, and that means, in other words, 180 degrees is a little more than 3 radians. You can see it right here on this diagram. The terminal side for 180 degrees would fall right here on the negative x-axis, but the terminal side for the angle of 3 radians doesn't quite get there. So if there's just over 3 radians in half a circle, how many radians are there in a whole circle? Well, if each half circle contains a little more than 3 radians, then a whole circle contains a little more than 6 radians. That makes sense? Now we're estimating here, and it's good to estimate because it helps you get a feel for how things work, but sometimes we need to be more exact. So let's see if we can get a more exact number for how many radians are in a circle. To do that, we're going to think about the circumference formula that you probably remember from high school geometry. A lot of us learned the circumference formula as the distance around the circle, the circumference, equals pi times the diameter. But so far in this course, we haven't really used the diameter for anything. We always talk in terms of a radius, right? So we know that a diameter is 2 times the radius. So sometimes you see the circumference formula written as 2 pi r. Now a lot of times in my classes, at this point, a student will often say, I thought it was pi r squared. So if you were thinking pi r squared, I just want to let you know that the formula for the area of a circle is pi r squared, but we're not talking area here. We're talking circumference, which again is the distance around the circle. So back to where we were. If the circumference is 2 pi times r, then exactly how many radius lengths does it take to go all the way around the circle? In other words, how many multiples of r are in a circumference? Well, you can look right here in the formula. There are 2 pi radius lengths in the circumference of a circle. So there are 2 pi radians in a whole circle. And if you think about it, this does match what we figured out with our approximations a few minutes ago. Remember we said that a whole circle would contain a little more than 6 radians, right? Well, 2 times pi would be 2 times 3.14159, etc., and that is a little more than 6. But if we're talking in exact terms, there are exactly 2 pi radians in a whole circle, and that means there are exactly pi radians in a half circle. So 2 pi radians is exactly equal to 360 degrees, and pi radians is exactly equal to 180 degrees. Now I know at first it may seem strange to you to count in terms of pi, but that's what we have to do to keep things exact. So if you're feeling like this is a little weird, you'll get used to it as we go along, but you just have to know we're going to be measuring radians in terms of pi. Now back at the beginning, we noticed that an angle of 1 radian is about 60 degrees, but now we can get a more exact decimal number for that. If we know that 180 degrees is exactly equal to pi radians, then we can divide and say 180 degrees divided by pi radians gives us approximately 57.3 degrees per radian. And now obviously because we're dividing by pi, we're going to get an irrational number here. So this has been rounded off, and that's why we have the approximation sign here. And that's also why we stay away from using this decimal number, because it is rounded, but we can stay in exact terms by just using the pi symbol. So that's what we usually do. Now we said before that pi radians is equal to 180 degrees, and that equivalence can be used as a conversion factor. We can make a fraction out of it, and we can have either pi over 180 degrees, or we can have 180 degrees over pi. And the way that you use it depends on which way you're trying to convert. If you have a degree measure and you're trying to convert into radians, then you're going to use it as pi over 180 degrees. On the other hand, if you have a radian measure and you're trying to convert into degrees, you're going to use it as 180 degrees over pi. The way I remember this is whatever unit I'm trying to convert into, that's what I need in the top. And you'll see why in just a second. So here's example 1, and it says convert each degree measure to radians. And in part A we have 45 degrees, and it says that we'll need to leave our answer in exact form, which means no rounded off decimals. So let's start with our 45 degrees, and let's think about which way we want to turn our conversion factor. We have a measurement in degrees, and we want to convert it into radians. So the way we need to turn our conversion factor is to have radians in the top and degrees in the bottom. And that allows the degrees to cancel out. And it's going to let our answer come out in radians. Now keep in mind there's no label for radians. So we have a degree symbol, but when we have an answer in radians, it has no label at all. You just have to know that it's radians. So 45 times pi over 180 gives us this fraction, and we are responsible for reducing this fraction. Now you might already know that 180 can be broken down into 4 times 45, and so when we simplify this fraction, 45 over 180 is going to reduce to 1 over 4, and we'll still have this pi symbol here in the top. So 45 pi over 180 reduces to 1 pi over 4. And so when you have a 1 in front of the pi symbol like that, it's like any other coefficient in algebra. We don't really have to write 1 when it is a coefficient. So although it's fine to write the result in this way, we will usually see it written as just pi over 4. And we know it's in radians, but again, notice there's no label that says radians. And then here in part B, we have negative 270 degrees, and again it says to leave your answer in exact form. So if we start with our negative 270 degrees, and again we multiply by our conversion factor as pi over 180 degrees, the degrees will cancel out, and we'll be left with negative 270 pi over 180. And now we need to simplify the fraction negative 270 over 180. Well, we know that 90 goes into both of these numbers, 90 times 3 is 270, and 90 times 2 is 180. So this fraction is going to reduce to negative 3 over 2, and we'll write negative 3 pi over 2. Now I hope most of you are comfortable simplifying fractions like this, but just in case you're not, or just in case you're in a hurry sometimes and you want the calculator to do it for you, I thought I'd show you how to simplify fractions on the calculator. So I've already done the step where we use the conversion factor, but now if I did not know how to simplify 45 over 180, what I would do is use the fraction button on the calculator to enter it in fraction form. So I'm not sure if everybody realizes this button right here is the fraction button. And so you can enter 45 fraction 180 and press equal, and it will simplify your fraction for you. How about that? And so you would take this and know that it's going to be 1 pi over 4, and when you write it down, you just know that you don't have to write that coefficient of 1. Okay, so how about the second one? It works pretty much the same, but because this is an improper fraction, there is one extra step that we're going to want to do here. So let's go ahead and enter our negative 270 fraction 180. And this time when you press equal, you'll notice that you get a mixed number. So it simplifies that fraction to negative 1 and 1/2. Now you could certainly convert that to an improper fraction yourself, but the calculator will also do that for you, because the second function of the fraction button right here, you can see it looks like it's converting a mixed number to just a plain fraction, and that is in fact what it does. So if you have a mixed number and you want to convert it to an improper fraction, you just use the second function of your fraction button. So let's go second fraction button equals, and there's our improper fraction. And just so you know, if you needed to go back to improper form for any reason, you can convert back and forth as much as you like. And so just as we saw before, this negative 270 degrees would be written as negative 3 pi over 2 radians. And now let's take a look at part C, which says convert 249.8 degrees into radians. And this time we're going to give an approximate answer, which means we're going to have an answer in decimal form, and it's going to have to be rounded off. Now the instructions here do not say how many decimal places to keep, but when you do your homework in my lab, again, they will have to tell you how many decimal places to keep, so always be on the lookout for that. So we're still converting from degrees into radians here. So we're still going to start with our 249.8 degrees, and we're going to multiply by our conversion factor in the form of pi over 180 degrees so that the degrees cancel. And now, since we know that we're going to be giving an approximate answer here, we know that we're going to need to enter the decimal form of pi here. So when you go to your calculator, you will enter 249.8 times the decimal value of pi, and here you can use the pi button on the calculator. For our TI-30X2S calculators, the pi button is the fourth button down the first column, and so you'll see it there. So you'll just enter 249.8 times pi button divided by 180, and that's going to equal approximately 4.36 radians. Now here in example 2, we'll convert the other direction. So here the instructions say convert each radian measure to degrees. And in part A we have 9 pi over 4 radians, and we want to give an answer in exact degrees. So again, that just means no rounded off decimals. So let's start with our 9 pi over 4, and this time let's take our conversion factor and use it as 180 degrees over pi radians. And remember, we want to turn it this way because we want our answer to come out in degrees, so we need the degrees part of our conversion factor to be in the top. Now when you write it that way, you can see that the pi symbols are going to cancel each other out. They're going to divide out. And we're left with 9 times 180 divided by 4. And you can just do that on your calculator, and you'll come up with 405 degrees. For part B, we have negative 5 pi over 6, And again, we're supposed to get an exact answer. And again, because we're converting out of radians into degrees, we'll use our conversion factor as 180 degrees divided by pi radians. The pi symbols will cancel out. And on your calculator, you'll enter -5 times 180 divided by 6. And that equals -150 degrees. Now, you may already know this, but I said -5 times 180 divided by 6. You could also do -5 divided by 6 times 180. Either way, you're going to get the right answer. As long as we multiply by whatever's in the top and divide by whatever's in the bottom, we can't go wrong. And then for part C, we have 4.25 radians, and we're supposed to give an approximate answer. So by that, we know that we will be using the decimal value of pi, and our answer will be a rounded off decimal. So let's start with our 4.25, and again, we'll use the same conversion factor, 180 degrees over pi radians. Now, you don't really see anything cancel out here, but we know we have radians in the top and radians in the bottom, and so our answer is going to come out in degrees. So on your calculator, you would just go 4.25 times 180 divided by pi, and that equals approximately 243.5 degrees. I kept one decimal place here, but as we've said many times before, whenever you're doing your homework in MyLab, always look for instructions that tell you how many decimal places to keep in your final answer. Now let's talk a little bit about exact form versus approximate form. As you just saw in part C of the last example, if a radian measure is not a multiple of pi, then the equivalent number of degrees will be an irrational decimal and will have to be rounded off. But most of the time in this course, whenever it's possible, it's preferable to stay in exact form. So we'll stay in exact form almost all the time, but as always, watch for instructions in MyLab that tell you which form to use. Now, I've mentioned a couple of times that radians do not have a label, so if no unit of measure is given, you must assume that the angle is measured in radians. And it really does make a big difference because here we have a 30-degree angle, but you know that a radian is much bigger than a degree, so an angle that was 30 radians would be much bigger than an angle of 30 degrees, and it would go around the coordinate system several times, and it would actually land in quadrant 4. So a 30-degree angle is a quadrant 1 angle, but a 30 radian angle would be a quadrant 4 angle. So that's why we say it's really important to be careful about what units your angles are measured in. And if an angle does not have a degree symbol, you need to assume that that angle is in radians. So we've seen now how to convert between radians and degrees, and it's not a horrible process, but we can streamline it a little bit, and that's what we're going to do now. So by memorizing just 5 basic conversions, we're going to be able to easily convert between radians and degrees for any angles that have special reference angles. So anything that's related to 30, 45, 60, or 90, we're going to be able to convert mentally and not have to use the conversion factor. We just have to know these basic conversions. So we already know that pi radians is 180 degrees. And once you have that, it's easy to see that if you divide both of these values by 2, you'll have pi over 2 radians equals 90 degrees. So pi equals 180 degrees. Pi over 2 radians equals 90 degrees. Now if you take this original statement and divide both sides by 3, the left side will be pi divided by 3, and the right side will be 180 degrees divided by 3, which is 60. So pi over 3 radians equals 60 degrees. Now do the same thing but divide both sides by 4, and so you find out that pi over 4 radians is equal to 180 degrees divided by 4, and so that would be 45 degrees. So pi over 4 radians is equal to 45 degrees. And then if you divide both sides by 6, you get pi over 6 radians equals 30 degrees. And so I'm going to go ahead and give you the steps, but this is one of those places in math where when you look at the steps it looks really complicated, but what we're going to do in reality is very easy. So let me go ahead and give you the steps. if you want to convert from degrees to radians, what you'll do is write the angle as a multiple of one of our special angles, and then exchange the special angle for its radian equivalent, which you will have memorized here. And then if you want to go from radians to degrees, what you'll do is exchange the special angle fraction for its degree equivalent, and then multiply the degree equivalent by whatever coefficient is remaining. Again, this will be much easier when you see an example. Okay, so here's example 3, and it says convert each angle to degrees. So we're going to start with 8 pi over 3. Now notice here that we have pi over 3, which is one of our special radian equivalents. So let's write this as 8 times pi over 3, just to help you isolate that pi over 3. And once you have your conversions memorized, then from memory you'll know that pi over 3 radians is 60 degrees. So 8 times pi over 3 radians becomes 8 times 60 degrees, which is 480. Let's try it on part B. So here we have 7 pi over 4, and let's separate the pi over 4. So 7 pi over 4 becomes 7 times pi over 4, and the pi over 4 radians is equivalent to 45 degrees. So 7 times pi over 4 radians is equivalent to 7 times 45 degrees, which you can do on your calculator, and that's 315 degrees. Now here in part C, we have 11 pi over 6. We can separate that into 11 times pi over 6, and we recognize this radian equivalent here. Pi over 6 radians is equivalent to 30 degrees. So 11 times pi over 6 radians becomes 11 times 30 degrees, and 11 times 30 is 330 degrees. Now here in part D we have 11 pi over 30, and you'll notice that 30 is not the denominator of any of our special angle equivalents. Our denominators were 2, 3, 4, and 6. So what do we do with a 30? Well, if you get one that doesn't have one of our memorized conversions, then you can just go back to doing it the old-fashioned way, the way that we learned at the beginning of the section. So you would take your fraction and you would multiply by 180 degrees over pi radians. The pi's would cancel out, and on your calculator you could go 11 times 180 divided by 30, and you would get 66 degrees. Or, now that you are used to swapping out the radian equivalents, you can just skip the conversion factor altogether. Now that we're used to exchanging radians for their degree equivalent, we can just notice that pi right here can be exchanged for 180. And so you can do it this way. You can say 11 pi over 30 is equivalent to 11 times 180 over 30. And then again you can use your calculator, or you might notice that 180 divided by 30 is 6, and so 11 times 6 would give you 66 degrees. So the important thing here is that you have choices, and I want you to be able to use the choice that's best for you. But don't be one of those people that says, well, I already understand the conversion factors, so I'm not going to learn anything else. I'm just going to always do it that way, because that way is good when you're first learning, but it will slow you down in the long run. So that's why I'm showing you how to do it mentally, because you're going to want to be able to do it quickly so you don't get bogged down. Now here's example 4, and in this case we'll convert from angles into radians. And the trick here is going to be to think of each degree angle as a multiple of one of our special angles. So we want to write each angle as either something times 30, something times 45, something times 60, or something times 90. So in this case, we have 150 degrees. And you can probably already see that this is easily broken down into 5 times 30. So let's write it that way. 150 degrees is 5 times 30 degrees. And we know the radian equivalent for 30 degrees is pi over 6. So 5 times 30 degrees becomes 5 pi over 6. And there's our radian equivalent. Now in part B we have negative 120 degrees. And here you have a choice. You could either think of 120 as 4 times 30, or you could think of it as 2 times 60. Now, whenever you have a choice, always choose the larger of the two, because that way you won't have to simplify in your final answer. So here we have negative 120 degrees. We're going to write that as negative 2 times 60 degrees. And then we're going to trade 60 degrees for its radian equivalent, which is pi over 3. So negative 2 times 60 degrees becomes negative 2 times pi over 3. And that is the radian conversion for negative 120. Here in part C, we have 270 degrees. We know that 270 is 3 times 90 degrees, and we know that the radian equivalent for 90 degrees is pi over 2 radians. So 3 times 90 degrees becomes 3 times pi over 2 radians. And then for part D, we have negative 315 degrees. Now, just the fact that it ends in a 5 tells you that it's going to have to be 45 times something. So you can figure that out on your calculator. 315 divided by 45 is 7. So negative 315 can be written as negative 7 times 45 degrees. And the radian equivalent for 45 degrees is pi over 4. So negative 7 times 45 degrees becomes negative 7 times pi over 4. Now I've got a little Quizlet deck in Canvas for you to help you drill yourself on converting between degrees and radians. So of course there's some practice in the homework, but not enough for you to really develop the skill as much as it needs to be developed. So do use the Quizlet set to help you drill yourself, and that way you'll pick up speed and you'll gain confidence, and it'll make things even easier for you later on. Okay, finally for this section here is example 5, and the instructions just say find each function value. And so we're going to be finding trig function values of angles measured in radians. Now we already learned how to do this for angles measured in degrees back in section 2.2. And so the best strategy for us to use is to convert these radian angles to degrees and then do it the way we learned how to do it back in section 2.2, or if the angle is a quadrantal angle, we'll use the unit circle. Let's start with part A. So we have the tangent of 2 pi over 3. So first let's convert 2 pi over 3 radians into degrees. You'll get to a place where you can do this mentally, but for right now I'm going to write it down. So 2 times pi over 3 becomes 2 times 60 degrees, and we know 2 times 60 is 120. So we're really looking for the tangent of 120 degrees. So let's draw ourselves a diagram of a 120 degree angle, and now we can see that the reference angle here will be 60 degrees. And so we know that the tangent of 2 pi over 3 will be the same as the tangent of 120 degrees, and we know that this is a quadrant 2 angle, so in quadrant 2 the tangent values are negative, so we'll put down our negative sign, and we know that the tangent of 60 degrees is square root of 3. So now we have the tangent of 2 pi over 3 radians equals negative square root of 3. In part B we have the sine of 3 pi over 2. So first let's figure out how many degrees this is. 3 pi over 2 radians is going to be 3 times 90 degrees, and that's going to be 270 degrees. So let's go ahead and draw ourselves a 270 degree angle, and we can see this is a quadrantal angle, and so we want to think about the unit circle. This terminal side goes through the point 0, negative 1 on the unit circle. So the sine of this angle is just the y-coordinate of this point. So now we can say the sine of 3 pi over 2 is equal to negative 1. And then for part C, we have the cosine of negative 4 pi over 3. So let's get a degree equivalent for negative 4 pi over 3. We know that pi over 3 is equivalent to 60 degrees. So negative 4 times 60 degrees is going to be negative 240 degrees. Now, you could probably draw that on a coordinate system, but let's go ahead and add 360 degrees to it to get a positive angle, because those are just always easier to draw. And so now we can see we've got the same diagram we had in Part A. We've got a quadrant 2 angle with a 60-degree reference angle. So the cosine of negative 4 pi over 3 is going to be, first of all, negative, because cosines are negative in quadrant 2. And then the number part is going to be 1/2, because the cosine of 60 degrees is 1/2. And so we end up with the cosine of negative 4 pi over 3 is equal to negative 1/2. Okay, that's all we have today for section 3.1. Now this is a big important section. Although it wasn't that long, it really is super important. So like I said before, really practice hard on getting good at converting between degrees and radians, especially the mental conversions that we did using our special angle equivalents. Most of what we'll do for the rest of the course will be done in radians, so it's really important for you to get comfortable working in radians. And when you go on to calculus, those of you who are going to take calculus, everything will be done in radians. So it's super important that you understand radians and that you're comfortable working with them. And that's it. So I'll see you guys again in section 3.3 next time. Bye now.